Python's Global Interpreter Lock, or GIL, is a mechanism that restricts multiple native threads from executing Python bytecodes simultaneously. This means that even if you have a multi-core CPU, Python threads will only run on one core at a time for CPU-bound tasks. In AI data preprocessing, this can be a bottleneck, especially when heavy mathematical operations are involved. To overcome this, engineers often use the multiprocessing module or rely on libraries written in C++, such as NumPy and PyTorch, which bypass the GIL and allow true parallel processing. Understanding the GIL is crucial for optimizing performance in AI workflows. When working with lists of feature vectors in Python, it's important to know the difference between shallow and deep copies. A shallow copy creates a new container but references the original child objects, so changes to the copy can affect the original. In contrast, a deep copy recursively duplicates all objects, ensuring complete independence. For example, if you have a batch of images and make a shallow copy, altering a pixel in the copy will change the original batch, potentially corrupting your training data. Using deep copy prevents this, safeguarding your input data for AI models. Python's short-circuit evaluation in conditional statements can help prevent errors like index out of bounds. In AND expressions, evaluation stops if the first operand is false. In OR expressions, it stops if the first operand is true. This is especially useful in AI data parsing, such as checking token sequences in NLP tasks. For example, if you check if an index is within bounds before accessing a token, Python will skip the second check if the first fails, avoiding an index error. This logical structure ensures safer and more efficient code execution. Modifying strings using concatenation inside loops is highly inefficient in Python because strings are immutable. Each concatenation creates a new memory block, copies both strings, and destroys the old ones, turning a simple loop into an O and 2 operation. In AI text preprocessing, especially when handling large corpora, this can cause severe delays. The recommended approach is to append substrings to a list and join them at the end, which executes in linear O(n) time. This method is standard in industry for efficient text processing. Python, the equals operator checks for value equality, meaning it compares whether the contents of two objects are identical. The is operator, on the other hand, checks for object identity, verifying if two variables point to the exact same memory address. This distinction is crucial when comparing tensor configurations or hyperparameter blocks in AI projects. For example, two dictionaries with the same values will be equal with equals, but is will return false unless they are the same object. Understanding this helps prevent subtle bugs in code. Python's dynamic typing means variables are simply names pointing to references, not containers of data types. The objects themselves carry type information in memory. This allows a variable to point to an integer at one moment and a string at another, with Python automatically updating the reference and managing memory. In AI workflows, this flexibility is useful for handling diverse data types, such as switching between numeric targets and categorical labels. Understanding dynamic typing helps manage memory efficiently and avoid unexpected behavior. Python optimizes memory usage by caching integers in the range -5, 256, and in turning short strings that resemble identifiers. When you initialize variables within this range, Python reuses the same object reference, saving significant RAM. In AI data pipelines, this is especially beneficial when labeling datasets with millions of rows using status integers like 0 and 1. All those pointers reference the same cached objects, reducing overhead and improving efficiency. This optimization is a subtle but powerful feature for large-scale data processing. Using a mutable object as a default argument in a function can lead to unexpected behavior. The default argument is evaluated only once when the function is defined, not each time it is called. This means all calls share the same instance of the mutable object. In AI inference tracking, if you use a list as a default argument, it can accumulate results from past users, causing data leaks across jobs. Always use immutable defaults or create new objects inside the function to avoid this pitfall. Python's for, else and while. Else loop structures can simplify logic in neural network convergence validation. The else block executes only if the loop completes naturally without hitting a break statement. For example, when checking for exploding gradients in a layer, if no gradient exceeds the threshold, the else block confirms stability and proceeds to optimization. This structure provides clear, concise logic for handling special cases in AI training routines, making code easier to read and maintain. Python passes references to objects, not copies. When you pass a mutable object like a list or dictionary into a function, any modifications inside the function affect the original object outside. In AI workflows, this can lead to accidental data loss, such as removing items from a dataset during cleaning, which permanently alters the original data. Understanding this behavior is essential for safely managing training and evaluation datasets, ensuring data integrity throughout your pipeline. Comprehensions in Python are optimized to run at sea-level speed, using efficient bytecode instructions that skip the overhead of loading the append attribute on every iteration. This makes them significantly faster than standard for loops, especially when scaling target labels or processing large datasets. In AI projects, using list comprehensions can accelerate data transformations, improving overall pipeline performance. Choosing the right structure for your code can make a noticeable difference in execution speed. Python lists are dynamic arrays, so appending or popping elements from the front takes linear O(n) time due to shifting elements. The collections, deck is a doubly linked list optimized for constant O(1) appends and pops from both ends. In AI time series models, using deck for rolling window buffers allows efficient management of real-time metrics, such as computing moving averages over thousands of time steps. This architectural choice enhances performance in sliding window algorithm. Python allows you to pass an arbitrary number of positional and keyword arguments into functions using args and asterisk quargs. Args packs positional arguments into a tuple, while asterisk quargs packs named keyword arguments into a dictionary. This flexibility is valuable in AI frameworks, enabling abstract interfaces for optimization algorithms with varying configuration. By using these features, you can design robust, adaptable initialization wrappers for complex training routines. Dictionary keys in Python must be hashable, meaning their hash value remains constant throughout their lifespan. Lists are mutable and cannot generate a stable hash value, so using them as keys raises a type error. In AI applications such as mapping coordinate points to classification labels, you must convert lists to immutable tuples to use them as valid dictionary keys. This structural constraint ensures reliable mapping and prevents runtime errors. Python set mathematical operations such as intersection, union, and difference use underlying hash maps to compute relations in near-linear time. This outperforms manual loop filtering for deduplication tasks. In AI text processing, finding common unique vocabulary tokens across documents is efficient with set operations. For example, using set intersection quickly identifies shared tokens, streamlining preprocessing and improving performance in large-scale data tasks. Zip function combined with the unpacking operator allows you to unzip a dataset of paired features and labels. By passing an unpacked sequence of pairs to zip asterisk paired sequence, you can separate corresponding elements into individual sequences. In AI evaluation, this technique is useful for splitting datasets structured as pairs into distinct arrays for features and labels, facilitating streamlined data processing and model evaluation. List sort method modifies the existing list in place and returns none, while the built-in sorted function leaves the original sequence untouched and outputs a new sorted list. In AI workflows, this distinction is important when sorting prediction probabilities for confidence inspection, without altering the original matrix order needed for index tracking. Choosing the right sorting method ensures data integrity and proper result analysis. You can implement a last in first out LIFO stack structure in Python using basic list methods. Use to push items onto the stack and pop, without an index to remove the most recently added item in constant O(1) time. This approach is efficient for tracking historical operational states during recursive tree search traversals and decision algorithms, making it a practical choice for AI application. Collections counter is a dictionary subclass designed to count hashable objects. Its most common K method runs in O(n) log K time using a heap implementation to extract the highest frequency elements. In AI text analysis, counter helps identify the top frequent words in a corpus, building primary vocabulary maps for tokenization. This tool is essential for efficient frequency analysis and feature extraction. Built-in filter function yields a lazy iterator that evaluates elements on the fly, while a conditional list comprehension computes and returns the entire filtered list immediately. In AI object detection, filter is useful for streaming high-confidence bounding boxes without loading all results into memory. Choosing between filter and list comprehension depends on memory constraints and processing needs in your pipeline. Python resolves variable names by searching scopes in a strict order: local, enclosing, global, and built-in. This LEGB rule ensures that variables declared inside a function shadow global definitions, preventing accidental overwrites. In AI model initialization, declaring a local learning rate variable overrides the global one within the function block. Understanding scoping helps avoid conflicts and maintain clean code structure. You can enforce keyword-only arguments in Python functions by placing an asterisk in the parameter list. This forces all subsequent arguments to be passed explicitly as named keywords, improving code clarity and preventing assignment errors. In complex AI training loops, this ensures parameters like epoch and learning rate are assigned correctly, reducing bugs and enhancing maintainability. Iterating massive nested sequences with multidimensional lists in Python can lead to significant memory overhead. Each row and cell element is a distinct object wrapper, consuming more RAM than contiguous arrays. For example, storing a 10,000 x 10,000 matrix with nested lists can use up to 10 times more memory than an equivalent NumPy array. Choosing the right data structure is crucial for efficient memory management in AI projects. Using a context manager with open is preferred over manually invoking file close in production environments. The context manager ensures the exit cleanup code runs automatically, even if an error occurs, preventing resource leaks and file corruption. In AI logging, this guarantees that files are safely closed, even during unexpected interruptions, maintaining data integrity and reliability. Enter and exit magic methods are essential for creating custom context managers in Python. Enter handles resource allocation and returns the target object, while exit manages cleanup and receives exception arguments. In AI workflows, custom context managers can connect to remote GPU clusters before training and safely disconnect afterward, ensuring robust resource management and error handling. Python's exception propagation mechanism handles unhandled runtime errors within nested function calls by traveling up the call stack. If an exception is not caught locally, it moves to the parent environment until a matching except block handles it or the program aborts. In AI pipelines, unhandled exceptions can halt system training runs, making robust error handling essential for reliable operation. Value error is raised when a function receives an argument with the correct data type but an invalid value. Runtime error is a generic exception used when an error doesn't fit other categories. In AI data validation, a value error is appropriate for invalid input dimensions, while runtime error is used for issues like GPU memory failures. Proper exception selection improves debugging and code reliability. Python caches modules in sys modules after the first import, preventing circular dependency errors during initialization. Subsequent imports look up the module in the cache instead of rerunning the file. In AI projects, this avoids issues when modules import each other, ensuring stable initialization and preventing attribute access errors before modules are fully loaded. Built-in Interactive Debugger (PDB) allows you to inspect code states on the fly by placing a breakpoint call. This pauses execution and opens a terminal environment where you can step through lines, evaluate expressions, and inspect variables. In AI preprocessing, PDB helps investigate issues like NumPy values without restarting lengthy data loads, streamlining debugging and development. Init pyfile marks a directory as a package and manages initialization steps. In modern Python, it exposes specific submodules and controls what gets exported during import operations. In AI frameworks, this enables clean mapping of functions like evaluate to internal modules, organizing project structure and simplifying imports for maintainable codebases. Safely append logs to an existing text file without overwriting historical information. Open the file in a append mode. This moves the file pointer to the end, preserving existing data. In AI training runs, appending metrics at the end of every epoch ensures that all tracking information is retained, supporting robust monitoring and analysis. You can write custom exceptions in Python by extending the base exception class and defining custom initialization properties or error descriptions. In AI projects, custom exceptions like data drift exception allow precise domain error handling, improving clarity and control over error management. This approach supports robust, maintainable code for complex workflows. Sys pathlist specifies the search path for modules in Python. If a directory isn't listed, Python throws a module not found error. In AI projects, sys path is critical for resolving custom imports across directories, such as running verification scripts that need access to core engines. Proper configuration ensures smooth module loading and prevents import errors. Python offers several methods for reading text files. Read loads the entire file as a single string readline, fetches one line at a time, and readlines reads the file into a list of lines. In AI data processing, using readline or iterating over the file object avoids memory overload when handling massive datasets, while readlines risks crashing by loading everything at once. Conditional check name == main determines if a Python script is being run directly as the main program. If the file is imported elsewhere, code inside this block will not execute. In AI utilities modules, this allows test routines to run only when executed directly, keeping imported functions clean and focused for production use. Merge combines changes from one branch into another using a single merge commit, preserving historical context. Git rebase rewrites history by moving the base of your feature branch to the tip of the target branch, creating a linear sequence of commits. In AI development, use rebase to clean up local feature branches before pull requests and merge for shared branches to maintain stability. Basing on shared public branches rewrites commit history, replacing old commits with new ones. If other developers are building on those commits, their local history diverges from the remote server, causing synchronization issues. In collaborative AI teams, rebasing the main branch can require complex manual resets, so it's best avoided to maintain consistent environments. Git merge conflict occurs when two developers modify the same lines of code in a file across different branches. Git cannot automatically determine which version to keep, so it pauses the merge and inserts conflict markers directly into the file. Resolving conflicts involves deciding which changes to keep, removing markers, and committing the resolution. This process is common in collaborative AI development. Git ignore file tells Git which files or directories to ignore, preventing local files and security risks from being pushed to a remote repository. AI developers should configure Git ignore to exclude large raw datasets, model weights, virtual environments, and sensitive credentials. This practice protects privacy and keeps repositories clean and manageable. Git fetch downloads the latest commits and references from a remote repository without modifying your working directory. Git pull runs fetch and immediately merges updates into your current branch. In AI development, use fetch to preview updates without overwriting local changes, and pull when you're ready to integrate remote changes into your workspace. Detached head state in Git means your workspace points directly to a specific commit hash rather than a branch name. Any new commits made in this state won't belong to a branch and can be lost. In AI projects, if you check out a previous commit to test an older model version, create a new branch immediately to safely make changes and preserve your work. Throughout this video, we've explored essential Python concepts for AI, including memory management, data structures, file handling, and collaborative workflows with Git. Understanding these fundamentals empowers you to build robust, efficient, and maintainable AI pipelines. By mastering these techniques, you can optimize performance, ensure data integrity, and collaborate effectively in modern AI projects. Applying these Python fundamentals in real-world AI projects means choosing the right data structures, managing memory efficiently, and handling exceptions robustly. Use context managers for file operations, optimize loops with list comprehensions, and enforce keyword-only arguments for clarity. In collaborative environments, follow Git best practices to avoid conflicts and maintain clean histories. These strategies ensure your code is reliable and scalable. Mastering Python fundamentals is a stepping stone to advanced AI engineering. As you deepen your understanding, you'll be able to tackle more complex challenges, optimize pipelines, and contribute to collaborative projects with confidence. Continuous learning and practice are key to staying ahead in the fast-evolving field of AI. Embrace these concepts and keep exploring new tools and techniques. With a solid grasp of Python's core concepts, you're ready to advance to more specialized AI topics such as model development, data engineering, and deployment strategies. Keep experimenting, refining your skills, and collaborating with peers. The journey in AI is ongoing, and every new project is an opportunity to learn and innovate. Stay curious and proactive as you move forward.